So this talk comes out of a conversation on an investigation we had in the office a month or two ago. We were trying to work out some oddity about how a particular system call behaved in the face of incoming signals and stuff. Joanne, I think, is on the call as the person I had the conversation with. But we kind of, as I was going through the actual machinations of working out what was actually happening, it turned out I knew much less about how all this stuff worked than I thought I did. So I just thought I'd kind of share the study that I did. This is about signal handlers, and I'm excusing the fact that this is more about Linux and Unix than C, because signal handlers are actually a feature of the C language, and it probably dates back from a time when the C language and Unix are pretty much the same thing and rolled together. So I'm going to start off with just kind of an example and just a little bit of a review on how signal handlers actually work. If anyone's got any questions, put them in the chat. I'll answer when I can, and shout if I ignore them or if I miss them. Okay. So this is a really simple, really basic program that just shows how signal handlers work. So you can see we've got a function which is called signal handler. It has just a printout to say that it's done something. And our main program just registers this signal handler so that when a signal arm is sent to the process, that the function gets called. Okay. And really what we're going to discuss is how this mechanism works and how we actually get from our main program into the signal handler. All right. This alarm system call basically says that there will be a signal arm delivered to the process in a second, and then we finally just hit pause, and pause just sits there until something happens. Okay. When we run a program, the pretty obvious thing happens. We see that we get a message from the signal handler to say that it received the signal, and then we see that the main function kind of sees that pause returns at -1, and error number is set to interrupted system call, or EINTR. All right. So if you look at the man page for any of these system calls, they'll often say that they'll return -1 for an error, and then they'll say that errno might be set to interrupted system call or some other thing, depending what the error was. When they talk about system calls returning interrupted system call, they're actually lying, and we're going to find out why. Okay. So just to note that when we are running a program here, that we don't actually have to be in a system call in order to receive the signal. So in this case, what we do is we don't call pause, we just have a loop that's busy spinning here. And even though we don't actually concede control to the kernel at any point in here, our signal still arrives and we still see that we get this done flag set and our program actually still sees the signal. Okay. So it's not that they're happening synchronously because of we've entered any kind of system call or anything like that. Even if the process is just running away, minding its own business, it'll still be subject to getting these signal handlers called. All right. Any questions or any issues there? All right, I'll keep going. So I'm not going to talk too much about how signals are actually sent into processes. We're just going to look more about how the processes respond to them. But just to go over like when signals actually get sent to processes, the obvious thing that happens is that some other process goes and kills a different thread, right? And this is when you type in kill on the command line and give a signal name, this is exactly what happens. A signal can happen from an asynchronous event. So if you have a timer goes off like a previous example, then at some point an interrupt handler kind of triggers and kind of marks the signal as being pending in the process. And the other thing that can happen is a synchronous event happens. So this is when a thread, say, seg faults because it accesses invalid memory or invokes an int3 instruction to hit the debugger or some other cases. All right. And when we're delivering the signal, there's a number of different states that the target thread might be in. Okay. And they're kind of, the first thing that we saw was our pause, where the system call was just kind of sitting there waiting for something to happen. So in that case, that process wouldn't have been on a CPU anywhere, it would have been just stopped in kernel mode, waiting for something to happen. And in that case, the process that's sending the signal can just mark that process now as being ready to run, and the scheduler eventually picks it up. And when the process runs, eventually it tries to return into user mode, and then the signal gets delivered to it at that point. The other case is when you're running, like in our while loop before. At that point, the code is your process is currently running executable code. Some other thread has come in and decided to send it a signal. So in that case, one CPU will send an inter-CPU message to the other, and that causes an interrupt. And again, the process will, when it's returning into user mode, invoke the signal handler. And then the final case is that you could be running in kernel mode. In this case, depending whether interrupts are blocked or not in the kernel, the same kind of thing happens. The kernel will check before it does any blocking operation to see if there's any pending signals, and eventually just return to user mode in order to have them delivered. All right. And that's it, I think. Okay. So The real question we want to answer is how do we get from running code in main or sitting in our pause system call to the point that we actually invoke this signal handler, all right? And one of the main things we have to think about, one of the main things to note here is that signal handlers for any system, for Linux, they're only ever delivered to the process. They only ever actually run when we're returning from kernel into user mode. So as the kernel, when you enter a system call, the kernel goes off and does whatever the system call does, and then it returns back into user mode. And at that point, it checks for signals. And if you get an interrupt, for example, some device interrupts you, your process stops pretty much immediately. And then as that interrupt handler finishes, the kernel will check again for signals and deliver them to you. So this is how we got things like, this is how the previous example, the previous comments kind of fall together, is that, you know, if you send an interrupt to another CPU, that actually causes an interrupt on the CPU, moves it from user land into kernel land, and then back again. And then at that point, you're checking for signal handlers. Okay. Any questions? Okay.
Just Peter, quick question.
Sure.
So you mentioned that it's you get an interrupt and it's the process is taken to the kernel mode and then back to the user land. Is it done immediately, or it waits in the scheduler to get back to the user land again?
No, it doesn't get scheduled out. So I mean, if you say you're running the program you saw before with just a tight loop in it, like there's regularly going to be interrupts happening on the CPU. So it could be like a disk activity finished or someone hit a key on the keyboard, right? And at that point, the CPU basically just gets interrupted, and it calls through this interrupt descriptor table, just calls some interrupt handler. The interrupt handler does what it needs to do, probably very little. So it might be just kind of putting something into a queue for later processing, and then it just returns back from kernel mode to user mode. So what generally happens in terms of the transfer of control is that the interrupt causes kind of a lookup into this interrupt descriptor table, and then unlike a normal kind of system, unlike a normal call instruction, you do things like modify the priority or the privilege level of the process, and then when you're finished with the function, rather than using a ret instruction, you use an iret instruction to return from the interrupt, and that just has slightly more of an effect on the system than a normal return instruction. But it's really just very like a call and a return. Yeah. Does that make sense?
I see. Okay. Yeah. Thanks.
Right. We'll see a bit more of this later on. Okay. So we're going to start off with doing some experiments with the original program we started with. So this is just running that program in the debugger. So the first thing that we do is we put a breakpoint in our signal handler and see what things look like when it hits there. All right. So we just run the program, and we see we hit our breakpoint pretty much immediately. And if we look at the stack in this case, it gets quite interesting. So we see our signal handler was called here, right? We can see the call into pause, which we had in our code. It comes out as libc pause just because of the way the debug symbols work. And we can see main here, right? So this is mostly a normal stack trace. We can see main, we can see it calling pause. And then in this frame, we've got this weird signal handler call thing. And then we have the signal handler itself, all right? So, you know, this is kind of where the magic sauce happens. And this is what we want to really work out, you know, how did we get this here and what is it, all right? So if we have a look at the frame itself, okay, here's frame one. So what we can do is we can print out the instruction pointer in this frame and see what's in it, all right? And when we print it out, we can see that it's actually this restore RT symbol, right? And that's actually code, so that we can see the disassembly of it. And what it does is it moves a constant into register RAX and then invokes this syscall instruction, all right? So one of the questions we really want to answer is like, where did this come from, right? We haven't mentioned it anywhere. It's obviously in our process. It's part of the user space of the process, all right? And then what's this actually doing here? So the other thing as well is that because if we look at the actual address of the instruction pointer here, it's exactly this value, right? And this is the start of this function. So there's no possible way this restore RT function could have ever called our signal handler, because if it had, there'd be a call instruction before this, right? Like normally, if you look at a stack, you'll see that as you walk down the different levels of the stack, the instruction previous to the one at levels below the first one are always just going to be call instructions, right? So this seems to be quite synthetic. There's something odd about how the stack is set up here, okay? And if we look at the system call table, so the way you call a system call is there's just an index for each system call, whether it's like get PID or fork or whatever, and that's used as an index into a table in the kernel. So what this is saying is you invoke system call 15, right? And if we look in the system call list in the include directory, we can see that that's rtsigreturn, right? So that seems reasonable. This is when we return from our signal handler here and we jump into this frame. If you think about what a ret instruction does when we return from the signal handler, it pops the first thing off the stack and just starts executing from there instead. All right. So in this case, we're just going to start executing this restore RT function, and we can see that what it does is makes this call to our system call for rtsigreturn. All right. Making sense? Okay. Okay. So we looked at the debugger and see what happened when we hit the signal handler. So let's have a look at the actual flow of system calls that get executed when we run our program. So this is just the output from strace on the process. Okay. So you can see the normal kind of machinations of the dynamic linker starting up and loading libraries and everything. But once we get past that piece, we can see where, this is our program here, and here's the system calls that actually got called. All right. Now we can see alarm and pause are pretty much exactly as they are here. But rather than saying signal, we see this rtsig action, right? So the signal call, which is like a C standard call, as I say, it's ancient and it's quite a simple mechanism for handling signals. So as time went on, the API for signals kind of developed a lot. So at this point, the signal function here is not actually a system call anymore, and this libc would basically wrap this signal into this rtsig action call. Okay. On other architectures, this is all x86-64. Other architectures actually have a sig action function and an rtsig action function, and there's kind of these weird real-time signals that POSIX introduced. And for x86-64, there was just no reason to implement the old legacy style system call, so they just don't exist. Okay, and we can see some of the stuff that rtsig action gets sent into it. So we see there's an SA handler here, and this is pretty much just the address of our signal handler. There's a list of signals that you want to mask while this signal is being used. So it makes sense that when you're processing sig alarm, you don't want to get another alarm signal because you just recursively enter this, right? So this is just masking this signal off. Okay. And then we have these flags, and then we eventually have this thing called SA restore. Okay. And we're going to see a bit more about that later on. All right. So we're keeping that in mind. Okay. And then beyond that, we can kind of see, this stuff here, which is basically coming from the printf, trying to work out whether or not it's connected to a terminal or not. We eventually get our write for the receive line here. And then we see rtsigreturn as a system call. So this is what we looked at before with restore RT. It's basically return from the signal handler, hit that little small 3 instruction function, which calls the signal handler to return. Or calls rtsigreturn to be invoked. And you can see rtsigreturn is actually what returns this -1 EINTR. If you look at pause, which is the system call that looks like is returning -1, that's actually got this error code returned. Okay, so that's the main saying that it says pause return -1 set errno to EINTR. It didn't. It was actually this system call did that. All right. Any questions so far? Silence. Okay. Okay. So the other thing I want to do is actually have a look at what's going in to this rtsig action call. So again, in the debugger, we can basically just catch the invocation of this system call and run a program again. Okay. And we know that the way arguments get passed into the kernel, that I know that the first argument or to the second argument to the function is going to be this RSI register. So this is this, where is it gone? Kernel sig action structure. So this is what the system call is actually getting passed from libc. So libc is sitting in signal, and it as part of the implementation of the signal C library function, it calls the rtsigreturn action syscall, and this is what it's passing it. And here's our SA restore that we saw on the strace output. And we can see that the actual symbolic value for that SA restore was restore RT. All right. So this actually answers a question of, where did this restore RT come from on our stack? It's actually passed in from libc directly. Right. So our own program is what put this restore RT thing into the kernel, told the kernel about this restore RT thing, and the kernel organized have it on the stack where it was. And we're going to see more about how that actually happened later. All right. Okay. We'll move on. Gee, hold on, let me see. I think I have more to go here. Okay, so just have a, hold on. Bear with me for a sec. Okay, so just some extra details on kind of more modern kind of semantics for handling signals. This is kind of the same program we've been looking at, but instead of using signal, I'm going to use sig action directly, and we can see a few of the extra bits and pieces that we can get out of sig action as opposed to just calling signal directly. So we can set this flag when we're setting up the signal to say, please pass me extra arguments when you're invoking the signal handler. And we can see now that our signal handler, instead of just having the signal number here, it has a siginfo t structure and this void pointer. Right? And if you read the man pages, it says the void pointer is actually one of these. Okay, and this program, as I say, is pretty much the same as the other one. It does exactly the same thing, other than the fact that it sets this siginfo thing, and we call sig action directly rather than through signal. And if we see again in the debugger what these structures here look like, this uContext t and the siginfo t, they are here. The SI field is kind of information about the signal, and you can see, okay, we've got our signal number, but we also have things like for different types of signals as other information gets carried. So, you know, for sig child, there's things like the process IDs. For sig fault, there's the address that you faulted at, this kind of thing. All right. And then you've also got this uContext t structure. And in this, you've got other bits and pieces. But the most important thing to actually notice here is that this uContext t structure that gets passed into the signal handler has the set of general purpose registers on the CPU and the floating point registers. So this is the state of the machine right at the point that the signal was delivered. Okay, so this is the user land state. So the user land was in this particular state, system call or interrupt happened, and this is basically the state that will be returned to when the signal handler is finished. All right. Okay, so it's kind of worthwhile remembering that this structure looks like this, and that we have this other thing here, which is siginfo t. Where's it go? Yeah, the siginfo t here. All right. Okay, so what we really want to do is we want to kind of look at and see, okay, how does the kernel actually deliver the signal to the process, and how does it invoke the signal handler? And as I said, the reason that happens is because, or the point at which that happens is when the kernel returns from kernel mode back into user mode. And there's two main places that happens. It's basically either returning from an interrupt or returning from a system call. So we're going to look at the system call case. The case for interrupt handler is actually similar, and we kind of see the overlap between, or where the call stacks overlap between the two of them. But it's kind of interesting to see actually how the system call works. So we saw earlier on that in order to invoke a system call, what you do is you give a system call number, and you use that in order to indicate which system call you're going to call. And then the rest of the registers in the system will kind of indicate what the arguments are like. Okay, so when you actually call that or invoke that syscall instruction in userland, this is when you transfer control from user to kernel. And what happens in Linux is, or in x86 64 Linux, it's actually this entry point here, this entry 6 syscall 64 gets called. So there's a bit of assembly language in here, but it's really just in order to get everything sane enough that we can actually call this do syscall 64 function in C. And what it does is it organizes to make sure that the registers for the system, for the userland processor passed as a second argument. So really, we can see this is the actual switch. Where's it gone? Here, where we look up the system call table, which has things like open and close and fork and get PID and whatever, and index it by this number, and then just call it. All right. So this is the point where we actually decide which system call we're going to look at. We're not actually overly interested in this here, because what we really want to know is what happens when we finish. And we can see when we finish, we end up at this point here. All right. Okay, so let's have a look down through return slow path. Oh, it's interesting to note actually that the registers that are passed in here, notice they're not const. So in theory, you can modify these. And we'll see why that's important in a few minutes. All right. Okay, so let's have a look at this function that gets called syscall return slow path. It doesn't do a whole lot, but it does call, let me see, prepare exit to user mode. All right. And then prepare exit to user mode eventually calls this exit to user mode loop. All right. So just for the case of interrupt handlers, this is kind of where the overlap happens. Prepare exit to user mode is also called in this function here, IDT entry exit condor CU. And this is called inside this define IDT entry. And you'll see for all of the interrupt handlers that the kernel defines, they're all wrapped up in this define IDT entry. So this is the piece of code that's common between the two cases. All right. So exit to user mode loop then is our next point of entry that we're interested in. And it looks like this. Okay. So there's obviously a loop here, hence the name. And if we scroll through this, you can see there's just various bits and pieces that might need to be done when you're exiting back to user mode. All right. And one of them, finally, we've actually started to see something about signal handlers. All right. So this do signal is obviously of interest to us. So let's have a look at what that does. All right. Okay. So what does do signal do? Well, it checks, is there any signals pending? And if there's a signal pending, the information about the signal gets put in here. This kind of returns most of the information that you would have from the details that you would have set yourself by calling sig action. So it tells you what the signal handler is, signal mask, all this kind of thing. So if there is a signal pending, the information that particular signal is mentioned in here, and then we call handle signal. All right. If there's no signal pending, we fall through to this, and we'll have a quick look at this later on. So inside handle signal now. So at this point, we know that there is a signal pending and we do need to handle it. All right. We can see that the first thing that happens is we look, are we actually in the middle of a system call? So remember, this can get called from either an incoming interrupt, or while you're in the middle of a system call. And in our case, we're looking at the system call case. So we can see the first thing that happens is that we overwrite the AX register, which is what's normally used to return the errno from the system call. And we override it with this EINTR. Okay. Now, this is the actual register that we're going to restore later on. So again, these are the registers that got passed up all the way from do syscall 64. And these are the registers that are going to be installed into the CPU when you return from kernel to user mode. All right, so we're basically changing the error number that was previously set and making it this EINTR. All right, and then a little later on, we do this. Okay, and this is setup RT frame. And setup RT frame is where we actually do the magical work that we were looking at earlier on. And we can see that just after this, it's the signal setup done is called. And this is effectively where the kernel says, right, I've delivered that signal, it's done. Okay, so we can kind of see that there's obviously something interesting happening in here, right? Any questions about anything yet? Okay. So let's have a look at setup RT frame. So these are all kind of architecture specific functions, and you can see in this case that setup RT frame for x86-64 has a lot of these little switches and corner cases for different types of problems. So this is basically saying, is this a 32-bit process that we're looking at? So if it's a 32-bit process, the semantics are a little bit different. You can see that for 32-bit processes, it has this setup RT frame or else setup frame, and this is the difference between these real-time signal handlers and classic signal handlers that we have to worry about, because 32-bit Linux supported both, right? For x86, so we have this other one for x32, which is this weird 32-bit pointer, but 64-bit instruction set architecture that I don't think anyone really uses at this point. And then finally, we get this setup RT frame, which is the x86-64 case that we're most interested in. So this is the basic case, all right? Everything else above it is just coping with, you know, architectural variations and historic problems, okay? So now we end up in setup RT frame, which is here. And this gets kind of interesting as well. So we see, okay, get sig frame, all right? So this returns, we're getting this frame structure, which we can see as an RT sig frame. And this little user annotation means this is actually a pointer into memory that the user process is interested in. So it's not kernel memory we're looking at. This is actually part of the running userland process, all right? So there's no kernel data in here. This is all just going to be basically stored in the userland part of the process, all right? And what this will actually do is allocate enough memory for this object on the top of the userland stack. So it looks at the current stack pointer and then just basically says, well, I need this much space for the RT sig frame structure, and it leaves a little bit of extra space for what's called the red zone. But this is really just memory inside the userland process. Okay. And now what we can see is what we do with this frame. We can see all this unsafe put user. So what we're doing is we're actually moving stuff from the kernel into userland, right? So we put these flags, these links. I'm not sure what all of this does, but we do eventually do this thing where we say unsafe put user, and here's our SA restore. So we saw before this was the restore RT function. So this would be a userland pointer to this restore RT function. And we put it in here, right? Which is inside this frame thing that we've allocated on the userland stack, all right? We put in this sig context, goes in as well. So this is filling in this part of the frame structure, and it fills it in with the system registers, floating point registers. Okay, so this might be familiar. This is the same thing that we were looking at earlier when we were looking at the 3-argument version of the signal handler, all right? So this stuff here is pretty much just setting up all of that kind of state on the userland stack, right? And these are the registers again that we say we're going to use when normally for a system call when it returns. These are the registers that get restored into the CPU. All right. Now the next thing that happens is we start manipulating those registers. So we've already copied them out into the out into userland. So they're sitting on the stack now for the userland part of the process. And now we start manipulating the kernel copy. So the first thing we do is set DI to be the signal that's being delivered. And then we have these SI and DX arguments get past this info and UC. So what we're actually seeing here is we're seeing the arguments for a signal handler getting set up, right? This is the first argument of the handler. So that's how x86 64-bit passes arguments. The first argument goes in here. Next argument goes in here. This is that sig info thing that we saw as the second argument of the signal handler. The DX register is the third one. And then the next thing that we do is we actually set the instruction pointer in the registers and we set it straight to be the signal handler itself, okay? So at this point, what we've done is within the kernel, we've taken the details that we were storing about that signal and we've updated the registers that were passed in all the way from the do syscall 64 earlier, so that when we actually replace or return from kernel mode back into user mode, the registers that we actually end up running with are these ones here. So they actually end up jumping straight into the signal handler. All right. And this frame that we set up is actually on the stack just below the signal handler. So if we actually look at the type for that frame, it looks like this. So this is pretty obvious again. These are the two arguments that we're going to pass into the signal handler. Okay. And then we also have this p-ret code thing, right? And this is what we set to be the restorer thing, this restore RT. So what happens is that when the signal handler returns, well, this structure is the thing that's actually on the stack. So when you hit the return instruction, it pops the first thing off the stack, which is the first word in this rtsigreturn frame, and just jumps into that code, right? So this is how we basically got from the signal handler then back again. So if when we were looking in GDB originally, we saw the signal handler called, or the signal handler called stack frame. What we was actually seeing was this, right? And this is where we saw the content sitting on the stack. All right, these are the arguments into the handler, and they're just sitting on the stack below us. All right. So that brings us basically to the point that we've actually invoked the signal handler, and now we know when we return, the first thing that's going to happen is it's going to invoke that return the sigreturn system call. So that sigreturn system call looks like this. Sorry, hold on a sec. Okay, so basically, yeah, we exit basically from this point all the way back to entry syscall 64, where we restore those registers that we just set up when we invoke the signal handler. And all of the state that we need in order to go back to our main part of the user program is all sitting on the stack in the userland program. There's no kernel state at all modified by the fact that you're invoking the signal handler. As far as the kernel is concerned, it's just going back to userland, and it doesn't know that it's kind of nested any calls to the signal handler anywhere. It's just going straight into the signal handler itself, and then something else has to work out how to get the program back to where it was. Okay, so we finally get back out of our out of our signal handler, and we end up in this rtsigreturn function. Okay, and this is really just doing the opposite of what the setup RT frame is. It finds this frame on the stack, and then copies things like, you know, the user registers and flags back out of the userland stack back into the kernel copy of the registers. So then when this system call returns, which is actually rtsigreturn, it'll return as if it would return from the original system call that was called. All right. Make sense? Okay. And this is just the case for, you know, we still have to end up coming back to do signal as we come through the rtsigreturn call, and we can see it does kind of things like, okay, if we have to restart the system call, we can see that what happens is we just actually walk the instruction pointer back by 2 instructions. So this is in the case that, for example, you don't want to have system calls interrupted with like returning -1 EINTR. You can get them to automatically restart, and the way it does it is actually just, it's not particularly elegant. It just takes the instruction pointer that was previously set up and just walks it back by 2 instructions to get over the syscall instruction. So when it goes back to userland, it just immediately trap back into the kernel. All right. Okay, so that's most of what I wanted to talk about. So let's just to recap. So signal handlers are basically only ever invoked when returning back into userland. If a system call is interrupted by a signal, the signal handler is invoked as the system call exits. And while the handler is being invoked, all the state that you need to restore the process back to where it was when signal occurred is actually sitting on the user land stack. It's not in the kernel anywhere. Kernel doesn't care about whether the signal handler was invoked or not. And it's this rtsigreturn function that returns your -1 EINTR to your program. And that's what's responsible for restoring the state from that user land stack back into your process just as it returns. Okay. And that's me done. Any questions or comments or anything?
Interesting talk, Peter. Thank you. I was chatting a bit with Niall Douglas when I announced the meetup, and he mentioned that he has a proposal for the standard library to add some signal handling support. So I referenced the PDF in the chat, which he linked, and it's like super detailed. Like it's way over my head. I can't even pretend that I know any of that stuff, but it might be useful to some people. And I think maybe I'm wrong here, but I think on Windows it's like similar in a way with the way they do the structure exception handling and the vectorial exception handling. I've tried to dig into that at a certain point in the past, but kind of gave up.
I think the main thing is that you can't have the kernel responsible for holding on to all that state, as you kind of call nested signal handler. So I'd imagine there is probably something similar. Yes.
Yeah. Just yeah, I've never really had to deal with this in too much detail. Like.
Right. Okay. Okay, no more questions. I think I'm done.
Cool. Thank you so much.